Okay. So, guess we should get started. And like I said, if anybody's actually already gone online and looked at the notes, you'll notice that there's quite a bit to cover today. These notes are about 21 pages. So basically, don't count on getting out of here by 6 o'clock. So what I want to do is the first thing we're going to talk about, and a lot of this stuff is going to be review, and I think it's going to be pretty much review for everybody. And the first topic is dealing with vectors and matrices. And so this is basically going to be the linear algebra part of linear algebra that you guys should really know. And then what we're going to do is I use linear algebra as sort of a jump off to later on getting into tensors. And so when I say linear algebra, what I really mean is that it's going to start off with the linear algebra you know. It's going to go into some things dealing with tensors and dealing with different coordinate systems. And then we're going to actually have another week where we're going to focus on tensors and another week where we're going to focus on eigenvalues problems. So those are all kind of under the umbrella of linear algebra, but they're different weeks and different topics. And obviously those are too much to cover in 1 week. So the basic idea is you start off with this idea of what we call a linear vector space. In this linear vector space is essentially, it's a set of objects that are closed under certain conditions. For example, addition, where if you take one vector and you add another vector, the result is going to be a third vector. And so if you add vectors together to other vectors, you're always going to get vectors. And so therefore, that's why we call it closed under this operation. Another thing is multiplication by a scalar. So if you take a vector and you multiply it by a scalar, the result is going to be another vector. Another thing is that you have this null vector that exists, where the null vector has the property that if you add the null vector to a vector, you get back the original vector, where the magnitude of the null vector is equal to 0. And when we get into like higher dimensional vectors, and like if you talk about 4-dimensional space-time, a null vector is not just made up of zeros, but it has a magnitude of 0. So it's not the same thing as just saying a vector made up of zeros. You also have multiplication by a unit term. So if you take 1 and you multiply it by a vector, you get back a vector. And then you also have negative vectors. And the basic idea is if you take a vector and you add to it a negative vector, then you get back 0. And that, as you remember from your previous classes, is basically to take a negative vector, you just take your vector and you just basically take the arrow and put it on the other side. So it ends up, this is the negative like that. And so this is, so when we talk about vectors, we're really talking about this space of mathematical objects that have these properties, and that all of them are going to be closed under that. So when we're talking about vectors, we're not necessarily limiting ourselves to a certain number of dimensions or anything like that. So when another property that vectors can have, and this is very important to us, is something called linear independence. And what linear independence means is if you take scalars and you multiply them by vectors, okay? So I take each of these Greek for the scalars, and I'm going to use the Latin for the vectors, and I add them all together. And the result is going to be 0. If this only happens, so only if all of the scalars happen to be equal to 0, then they're linearly independent. And so the way you can think about that is, imagine you have two vectors. One I'm going to call y, and another one called x, okay? And you'll notice here that x and y, they're perpendicular to each other. So what happens is, if you multiply x by a scalar and you multiply y by a scalar, there's no way that those two are going to cancel out and give you 0 unless you multiply both of them by 0, right? But if I had 3 vectors, and let's say I had one like this, one like this, and one like this, now all of a sudden there's a way you can see that the middle vector here is a combination of the other two vectors. And because of the combination of the other two vectors, you can multiply the other two vectors by some scalar, you can multiply the middle one by some scalar, and as a result, you can get this to add up to 0, including using negative values or whatever. So linear independence is basically what later on leads us to ideas like orthogonality and leads us to the idea of multiple dimensions. Because each dimension, we're going to find out, is going to be linearly independent from all the other dimensions. Doesn't matter how many vectors you have going along the x-axis, they're never going to add up to one going on the y-axis. Okay. So what we say then, if you have n linearly independent vectors, but not n plus 1, then we call this an n-dimensional space. So the dimensions of your space depend on the number of linearly independent vectors you can have. A 3-dimensional space has got 3 linearly independent vectors, x, y, and z. You know, a 2-dimensional space like this board, you can only, like on the screen, you can only have 2 vectors that are going to be completely linearly independent from each other. They don't have to be in any certain direction. You can have them going like this, or you can have them going like this. Either way, they're still linearly independent, right? And so that's kind of the judge that we're going to use in defining the dimensionality of a space. And so if you have, say, E1, E2, all the way up to En, and these are n linearly independent vectors. Then, and let's say this is an arbitrary, you can create an arbitrary vector x by just combining these guys. So you can have, for example, lambda E1 plus mu E2 plus some other stuff all the way up to sigma En plus tau x equals 0. And so what happens is that all of these vectors can add up to give you x, essentially. And so we can say then that x is equal to just taking the sum over all the dimensions of each component times each one of these E vectors, or each of the linear independent vectors. And so when we do this, this becomes what we call a coordinate basis. And so we'll say that this E sub I is a basis vector. So it's a basis vector or coordinate basis. The x's here are components. So they basically just say how much of each basis are you going to use. And so now you can construct any vector you want by just saying that it is created by a linear combination of all of the linearly independent vectors you can possibly have in that vector space. And so if you're talking about a three-dimensional vector, then you need 3 bases, and then you can combine those 3 bases to give you any vector you want. If you're talking about Cartesian coordinates, that's x, y, and z. If you're talking about spherical coordinates, you could do that with r, theta, and phi, where you combine r, theta, and phi together, and you can create any vector you want in spherical coordinates. And so these bases right here, this is basically like x, y, and z. And the component just tells you how much of each one you need.
So the x in that case is just an arbitrary variable?
Yes. It's not just necessarily the x-axis, it's just arbitrary. And so the idea is that any vector x can be expressed in terms of each one of these bases, assuming you have a complete set. And a complete set means that you have every possible linearly independent vector captured. So for example, if I'm talking about a three-dimensional space and I only have 2 vectors, that's not a complete set, right? I have x and y, but there's no z, then I can't use that to create anything else in the room. And then you can randomly choose your basis. Your basis doesn't have to be orientated along a certain direction or anything like that. It can be whatever you choose your coordinate system to be. And what we normally do is we choose our coordinate system for mathematical convenience.
Is that x sub I in the summation, is that actually a vector? Or is it
no, that's a scalar. So it's just we call it a component. And the idea is if I'm going to create, let's say I have these 2 vectors to work with right here. And I want to create another vector pointed like this, then what I have to do is I'm going to have so much of this where I'm going to multiply this one by like a negative number, like say -1.5. And I might take this one, multiply by -1, add them together, and I got that vector. So that's all we're really doing. And the neat thing about this is we're kind of working backwards and trying to understand vectors from where they come from instead of just focusing on how to use them. So this is very, very visual compared to a lot of the other stuff we've done. So this brings us to the idea of linear operations. Or operators. And by the way, if you guys haven't figured out yet why they call this linear algebra, just kind of go back and look at the titles. Everything is going to have the word linear in it. And it's only later on we get into some serious nonlinear stuff. So what happens is we have a linear function or linear vector function is something that associates the vector x with some other vector which is a function of x. And it's got to be linear. And by linear, what we mean is that if you take this function of lambda a plus mu b, then that should be equivalent to taking lambda times phi of a plus mu times phi of b. In other words, what we're doing, and this is just kind of the more mathematical way of putting it, is that it takes a vector A and it maps it into a new vector, but it does it in a consistent way across any vector, so that if you have another vector right next to A that's almost the same as A, but just a tiny bit different, the new vector it maps it to is going to be just a little bit different. And you can see here that you can, if you add two vectors together inside the function, it's just like adding together the vectors, the results of that. Yeah, it's basically saying that the vector A maps into this vector phi of A.
Oh, okay.
Yeah. So kind of like, it's the function, and what I mean by mapping is like, it's just some operation where you could say, let's say you got a group of numbers in here, and you have another group of numbers here, and it literally takes a number right here, and it puts it over here. So it goes from here to here. So in other words, the operation that it goes through to get from here to here, it could be like, you know, squaring it, it could be multiplying it by 2, it could be taking a dot product, whatever. But what the result here, what this means is it's taking a vector and it's turning it into a different vector. But it's, because it's linear, it's doing it in a consistent way, so that the vector that was right next to x here, which I'm going to call g, gets mapped into a new vector, h, which is right next to y, or something like that. Yeah, yeah, and that's another point. You can actually reverse these and go backwards.
So does linear in that case imply that it's continuous, that every g has an h and vice versa?
Mm-hmm.
Okay.
Yeah, I mean, it should be continuous. So, you know, when we talk about nonlinear, that's when you get things where you're right next, you know, you can't map necessarily a function here is going to be consistently the same over here. And you can't just add two solutions together to get the third solution. So nonlinear would be like if this was not equal. Okay, but for our sake, we're only going to be dealing with the linear stuff. And yeah.
So is it also considered not equal if you have the coefficient inside of the function? Like if you have like phi a lambda plus phi mu b.
Phi a lambda times phi. Yeah. Yeah, you could switch the order on it.
Okay.
Yeah, I mean, if you had b plus a instead of a plus b, you could do that.
Well, I'm talking about putting the coefficient inside the function.
Oh, coefficient inside the function?
Yeah, like
Oh, yeah, you could do that.
Okay.
You could, I mean, all the scalar can move in and out of the function in this case. Because it's linear, it doesn't even affect the scalar. It only really responds to the vector.
Writing dB is your,
Yeah.
just kind of line the hopping out.
Mm-hmm.
You get like flashing properties.
Yeah. All right, so one thing you should note is that if you take this linear function of a basis vector, then it's the same thing as if you take some components and you contract it, or you sum it with the basis, where you're summing this over all dimensions. And so the idea is that phi here is a vector, right? And E here is a basis vector. And so what happens is when phi, because it's a vector, it's an arbitrary vector, it's a sum of the basis vectors, right? And so therefore, you can get some kind of relationship where what this is saying here is that if you take each one of these coefficients. See, I don't want the summation symbol here. So what this is basically saying is that if we take, for example, this could be 1I and then E1 plus A2I E2 plus A3I E3, something like that. And so what's happening is, you can think of this in Cartesian coordinates as x, y, and z. And A1, A1I, A2I, and A3I are like scalar values. So these, the only difference between these is that they depend on I, whatever it happens to be. So what they're saying is that if you put in E1 here instead of E2, the result is going to be different components, which are still going to be multiplied by the different basis vectors, and then result in a slightly different vector. And so what this operation could mean is something like you put in the x vector, and you get a y vector out. You put in the y, you get a z. Put in a z, you might get another x, or some combination of those. And so what this is saying is that, you know, for x, you get this set of components. For y, it might be a different set. For z, it might be a different set. And so this Ji in this case is the jth component of the linear vector function phi ei. Okay, and I know that's a little abstract, but this is one of these things that I'm going to kind of introduce, and then I'm going to go back and it'll become more clear as we move forward. So the idea here then is that if you have, say, a vector y is equal to phi of x. So in other words, I put in the vector x and into this linear function phi, and I get the vector y out. Now y is equal to phi times the sum over I of x sub I e sub I. And the reason why I write it this way is because, remember, x is an arbitrary vector which is made up of these components, x sub I and e sub I, the basis. So I can take this arbitrary vector x and I can expand it out. Now, because I've expanded it out, I can actually take the components for x, since they're just scalars, and I can move that outside of this thing. So I could say that this is just the sum over I, x sub I, of phi of e sub I, right? Now, from here, I know that I can write this phi of e sub I as just the summation involving these components. So I can write this as a sum over I, x sub I, as a sum over j of a ji e sub j. And that's just plugging this in. And so now what I can do then is I can also know that y is supposed to follow the same rules as x does, since it's also an arbitrary vector in some ways. So this is equal to the sum over, let's say sum over j of y sub j e sub j. So I have components and basis for y as well as I do for x. So this is also equal to the sum over I, x sub I, sum over j, a sub j, I, e sub j. Now if you look at the two of them side by side, you see the e sub j in both? Well, I can eliminate the sum over j, because it's in both, and I can eliminate the e sub j in both. And I end up with y sub j is equal to the sum over I, aj I, x sub I. In other words, I can relate the components of one to the components of the other. And so if you assume that x and y are written using the same coordinate basis, then you can basically change from one arbitrary vector to another one by just altering the components. And this tells you how to change the components. Oh, why does that come from? That came from the same logic as I used here for x sub I. I just changed i's into j's, and yeah. So I'm summing over j. I mean, since I'm summing over, it doesn't really matter what I call it, but I didn't want to call it I in both. Because if I called it I, then that would have implied I wouldn't have been able to argue the basis was the same. All right, so what this does is it basically tells us that we can change the components in order to change the vector. So now, it's almost as if you have y, the vector, is equivalent to just some arbitrary operator acting on x, where this is called the linear operator. And you notice I'm using a script A as opposed to just a regular A. And so Aij are then components of the linear operator. And so this linear operator basically tells us how to go from being one coordinate or one vector to another one. And so if we write this out, this is equal to, say, A11, A12, all the way over to A1n. And then this, you can actually go down, let's say A21, all the way down to AM1. And then you could even have, like, say, AMN. So that is the linear operator, otherwise known as a matrix. And so all the Aij's are just elements of that matrix. And so the way we think about it, we have linear vector spaces that are populated by these vectors. And in order to get from one vector to another, you basically use these matrices. And so matrices are just a vehicle to go from one vector to another. All right. So, everything's doing good? Everybody's good? Cubs are up 4-2, and we're all good? Okay. So far. It's only the third inning. All right. So, what happens is that you can actually do a lot of the same algebra with these matrices you could do with vectors. So, for example, if you sum over I times a matrix A plus a matrix B, JIX, that is equivalent to taking a matrix operation AJIX, or so just be I, plus the same, another matrix operation involving B. And so what happens is you just sum these two together and you get your transformation on that. And the reason why we can do that is because if you think about it, when you're doing this summation, you're literally creating a vector. And so by putting this arbitrary vector x in there, we're basically doing the same, just a vector operation. If you take, for example, AB, and you sum over, say, Ji of the combined matrix that it forms. This is equal to taking the sum over, let's say, L of AJL times BX forming a matrix. And so, and that is equivalent to the sum over both L and I of taking AJL times BLI XI. And so what this second one does is it basically gives us the formula for matrix multiplication. Because you could see for matrix addition, we're basically just going unit by unit, element by element, and just adding them together. For matrix multiplication, it's basically saying that when you look at this, you really have, to get the Ji'th element of the combined AB matrix, then you're going to take the jth row from A, and you're going to have the ith column from B. And so the number of columns in A has to equal the number of rows in B in order to even do this operation. Because otherwise the L's don't line up. And also you could see that that's why matrix multiplication doesn't commute, is because if you flip the order, the rows and the columns don't necessarily line up in number. Now in physics, in pretty much most of the problems you're going to run into, you're going to just see square matrices, and so the number of rows and columns are the same. But just in general, it's just good to know this. Now also you should note that if you just put in a scalar here, then the result is going to be lambda sum over I AJI XI. So basically the scalar just kind of just multiplies in with the matrix the same way as it multiplies in with the vectors. So these are essentially the mathematical operations you can do with the matrices. Now also another thing is that we should note that there is such a thing as a null matrix. And a null matrix is one where all the components are 0. And if you take a null matrix and you multiply it by a vector, you're always going to get 0. So basically like a matrix that just transforms your vector into 0. There's an identity matrix. And an identity matrix is basically it's the delta function where it's just simply ones along the diagonal. And then there's this inverse matrix. And the inverse matrix is one where if you take the inverse matrix, and that comes from taking the inverse matrix multiplying it by the matrix, and getting the identity matrix back. And with the inverse matrix, the order of the inverse matrix and the order of the matrix don't matter. So in order to have an inverse matrix, it has to be a square matrix. Otherwise, it doesn't work. And since the main thing we're using our matrices for is going to be like coordinate transformations to transform from one vector to another and things like that, we need to be able to transform them back, as somebody pointed out, if it's a linear operation, right? And in order to transform it back, that means you use the inverse matrix as opposed to the matrix. And in order for the inverse to exist, you have to have it has square matrix. And so because of that, we're only going to really be using square matrices here. Now, to calculate the inverse, this is a lot of work. The inverse of a matrix comes from calculating the cofactor of AJI, and you divide that by the determinant of A. Can anybody here remember what a cofactor is? Because I'm guessing you guys probably haven't even heard that word in a few years. A cofactor comes from if you take the -1 of the I plus J component, so you're thinking ith row, jth column, and you multiply that times the determinant of the matrix without row I and column J. So what that means is that if you're talking about a 3 by 3 matrix, then you've got to do 9 operations in order to calculate the inverse. Because you have to calculate the determinant of the matrix itself, which is not too bad, but then you're going to have to calculate the cofactors, so you got 9 of those. So you're going to take -1 times the I plus J. So for example, in the 1, 1 component, it's going to be just 1. In the 1, 2 component, it's going to be -1, and so on. And then you're going to just take out that row and column and then calculate the determinant of whatever's left over, which is not bad because you're basically just left with a 2 by 2 matrix you have to calculate the determinant of. Now imagine you're doing like a 100 by 100 matrix or something like that. That's when you get into some serious trouble. Actually, what you use there is Mathematica or MATLAB. Yeah, I mean you can. What happens is you can diagonalize the matrix, but that involves finding the eigenvalues and things like, which we'll get into next week. I think next week or the following week. I think the following week we'll get into that. But yeah, you can diagonalize it, and if you diagonalize it, then it's easy to find the inverse. If you can't diagonalize it, then you're running it's a little harder. So if you're lucky enough to have a diagonal matrix, you do that. But this is where a lot of the difficulty comes in with physics, is that you run into problems where the math just gets impossible or very difficult to do. And so you can see that once you calculate this inverse, then you can use that in order to calculate your the inverse transformation, or to use that, multiply it by the matrix and get the identity or whatever you want to do. All right, so what happens is that you can actually group matrices based on their properties. and based on how the inverse looks compared to the matrix itself. And the idea being that if you could kind of know the general properties of the matrix, then it's easier to work with, and you can kind of group everything together. And this is where the idea of group theory comes from. You know, when I think group theory, you know, there's group theory that we talk about in, you know, they might talk about in chemistry, and then there's group theory we talk about like in mathematics or physics. And what I mean is more the math physics definition of it. Where in physics, the concept of group theory comes more from the mathematics, where you have different groups. In case of like particle physics, they actually look at symmetries, and if things transform under certain symmetries, then they're grouped in together. So, for example, if you have a matrix A, you say it is real if you take the complex conjugate of the matrix and it's equal to itself. And you know, that makes sense, right? You could say that it is symmetric if you take the matrix and you transpose it and you get itself back. It is anti-symmetric if you take the transpose and you end up getting minus the matrix. It is Hermitian if you take the A dagger, which is the transpose and the complex conjugate, wrapped together in one, and you get itself back. Now, Hermitian, I don't know if anybody's ever heard of that term before. Hermitian is actually one of the most useful out of this whole group when you're doing physics. And the reason why is that in quantum mechanics, every operator that you use is going to be Hermitian, because a Hermitian operator always yields a real eigenvalue. And a real eigenvalue is something that's actually observable. So that's kind of, quantum mechanics depends on these things being Hermitian. You've got orthogonal, and that's where if you take the inverse, it is actually equal to the transpose. So the transpose is equal to the inverse. Then there's unitary. And unitary is when the inverse is equal to A dagger. So you can tell that, you know, something can be orthogonal and unitary, especially if, because the A dagger could be equal to the transpose, assuming that, you know, the matrix is also real. But unitary is a much more broad definition there. And then, of course, you have diagonal. And diagonal basically means that Aij is equal to 0 if I is not equal to j. And remember that the transpose comes from when you take Aij and you turn it into Aji. You flip the rows and the columns. So the only other thing I didn't define here was idempotent, which is something I've not really even used any of these for. But the rest of these are properties of the matrices that you kind of will run into and use a lot. Yeah. Well, diagonal? yeah. Idempotent.
The one that you talked about, the A.
Yeah, the idempotent. Yeah, I have not really seen it come in useful. Just, you know, just from physics problems and stuff, I just haven't seen it. But like everything else, like I said, you know, especially if you're doing, when you get into quantum mechanics, you're pretty much using all these with the matrices. And if you get into like group theory or you know, advanced quantum mechanics or quantum field theory, then you're definitely going to use it. Okay. Also, just going back and defining a few simple terms, the trace of a matrix, it just comes from summing terms right down the diagonal. And so to do a trace, for most of these operations are going to require a square matrix. Doing a trace definitely requires a square matrix, but you can see here that if you have a diagonal matrix, this is a lot easier, calculating a trace. Also, you know that if you take three matrices, A, B, C, and you calculate their inverse, it's the same thing as taking the inverse of C times the inverse of B times the inverse of A. If you take the transpose of the three, it is like taking the transpose of C times the transpose of B times the transpose of A. And if you take the trace of A times B, it's equal to the trace of B times A. And if you take the determinant of A times B, it's the same thing as taking the determinant of A times the determinant of B, or the determinant of B times A. So either way, you're kind of in good shape. All right. Next thing I want to get to, I'm actually going to skip the part about dividing matrices into blocks, because that's really not as useful. But what I want to do next is I want to get into coordinate transformations, and then I guess we could take a little break before we get into eigenvalues. I'm going to briefly into eigenvalue problems. And then after the eigenvalues, because the eigenvalues are going to be kind of a lead-in to, let me see where we are. Actually, you know what, we'll take a break after the eigenvalue problem. Okay? So we got about a good 15, 20 minutes at least, and then we'll take a break. All right, so this brings us to coordinate transformations. Okay, so for coordinate transformations, we start off where we talked about before, where you had this component y, where you could say that, let's say, I'm not going to talk about, I'm talking about the vector y. So this is an arbitrary vector, and I'm going to leave this indice on here to say that this is just, you can write out each of the components of the vector. And this is equal to the sum over I of A, J, I, X, I. So in other words, the matrix is transforming the vector from one vector to another one, okay? Linear transformation. And you can think of, if this is a matrix, then I, X and Y are both single column matrices. And so the idea then is that if you have these column as opposed to row matrices, and you can multiply row, column by column, and multiply the matrix by column and get another column. So if this works for the matrix, or for these vectors, then what happens is you can assume that they should also work for the basis. So the basis, let's call this E prime J, is equal to the sum over I of what we're going to call a transformation matrix, gamma ij, E sub I. And so what this means is that we can transform from one basis to another by just simply using a matrix. And what that means is that we can take a system where our basis vectors are written like this and turn them into a system where our basis vectors look like this. And that would just be a simple rotation. And so here, this gamma matrix is the ith component of E prime j in the E system. And so you can think of it as if you take a vector, I'm going to get another page for this. Take a vector x. It is equal to the sum over I of x sub I E sub I. And that is equal to, that is basically your arbitrary vector x. Now we can also express this arbitrary vector x using a different basis. So we're going to call this x prime sub j, E prime sub j. Okay? So this is x expressed in terms of the non-prime basis, and this is x in terms of the prime basis. And so another way to look at it is, in this particular coordinate system right here, I could create an arbitrary vector x that looks like that. And I can express that vector as the sum of these two bases. Or, in the new coordinate system, I got the same vector, but it has to be expressed in terms of a different basis. So that's all I'm doing, is just changing the basis, but expressing the exact same arbitrary vector. So, since I can transform from one basis to the other, I can take this prime basis here and I can rewrite it as sum over j of x prime j times the sum over I of gamma ij E sub I, right? And so if we look at this, we've got the same E sub I in this equation and the first equation and the last equation. And so I can just simply get rid of those terms, and I could say, well, x sub I, therefore, must be equal to the sum over j of gamma ij x prime j. So in other words, I can transform the components just like I could or I could transform the basis however I want to do it. And so we can also write this as just x is equal to gamma x prime, which basically means that we have this transformation matrix that transforms from one vector to the other. And that also can be written where if we take the inverse of the matrix, then we could say that, well, gamma inverse of x is equal to gamma inverse times gamma x prime. And then you can see the gamma inverse and the gamma, they give you 1. So this is just x prime. And so we say that x prime is equal to gamma inverse x. And so what we get from that is that we can transform and transform back between different coordinate bases. And so I use the example of a simple rotation, but this can also get us from Cartesian coordinates to spherical coordinates to, we could transform to any coordinate system we want. any of them that we can imagine. And typically what we're going to do is we're going to just find the coordinate system that's just the simplest, that makes the math easiest and the least headachy for us, and we're going to transform to that system.
So that's what the gamma function is for.
Yeah. Yeah, so in this case, the transformation matrix, which it's not always a gamma, but I'm just using a gamma here. Another thing you can do is we could say, for example, y is equal to ax, where A is like a transformation matrix transforming from x to y. And then y prime is equal to A prime x prime. Okay? And so this is basically, in the prime coordinate system, there's a different, let's say there's a different transformation to go from here to here in a different basis. So what we could do is we could say, well, gamma times y prime is equal to y, and that is equal to ax, and so that must be equal to a times gamma x prime. And so then you would multiply both sides by the inverse. So you have y prime is equal to inverse gamma a gamma x prime. And so, and that in turn is equal to a prime x prime. And so therefore, you could see that to transform the matrix, we're actually using like this sandwiching, where you take the transformation matrix and its inverse and you sandwich the matrix between it, and that transforms the matrix. Or you can flip it around and you can say that the matrix comes from taking gamma A prime inverse gamma. And this is known as a similarity transformation. And essentially how that works is that you really, it's like one matrix is transforming the rows and the other is transforming the columns, the way I like to think of it. And these are linear operations so that they can add together. And so, for example, I guess I gave one example in the notes where you could have something like matrix A, B, C plus lambda D. And this can be written where you can actually do similarity transformations on each one of the components. And then you can see that this is going to be like lambda S inverse DS. And then all that does is basically turn this into A prime times B prime C prime plus lambda D prime. Now, what this does for us is that it allows us to see that the laws of physics are going to be the same in all the different coordinate systems. Because even though we're doing all these transformations with the coordinates, it doesn't alter the equations. And this is actually one of Einstein's big contributions in how he came up with special relativity, was figuring out a transformation that you can go to get from one system to another, which preserve the laws of physics between them. Okay. So for a vector, it needs a transformation matrix and it changes. For a matrix, you need to put two transformation matrices in there in order to transform it. What about scalars? Any ideas?
Transform I think it's easier.
No, you don't need to. Scalar, it doesn't matter what the coordinate system is, it's the same value. And so a scalar shouldn't need anything to transform. So let's suppose we have a scalar linear operator. Oops. Sorry. Used to writing vectors. So this is going to be just a scalar operator, phi of x. And a good example of a scalar operator is something like temperature, where if you can imagine in this room, you know that the temperature is not 100% uniform. You've got a really accurate thermometer, and you went around the room at different locations in the room. You measure slightly different temperatures, right? And you can kind of create a map of where all the temperatures are different. Now then, if you change the coordinate system, it shouldn't change anything. It's still, because there's no direction or anything dealing with that. But if you do magnetic field or something like that, then all of a sudden you change the coordinate system, you have to re-express everything. So the idea is if we do this with the scale and we're doing it right, we shouldn't see any change. So we have this linear scalar function, and it is basically equal to taking phi, that's an arbitrary vector, and so I'm going to write that as a sum over I of the components times the basis. And so we're going to express this as just the sum over I of a sub I x sub I, because this is going to result in a scalar. And a sub I in this case is equal to phi e sub I. And so what's going to happen is phi of x is equal to alpha x. Because, again, this is a scalar and we're looking for a scalar. Phi prime of x is equal to, of x prime is equal to alpha prime x prime, which is equal to alpha prime, and then I could say this is going to be the inverse transformation of x, which is equal to the similarity transformation, effectively, inverse gamma phi of x phi, because all I did here was I just said, well, I've already got this transformation, I'm going to just throw another one on. And then what happens is, since this is a scalar, it just commutes through, and then you have the inverse gamma times the gamma, and that just gives you 1, so this is just equal to phi of x, which is equal to alpha x. And so that tells us then that if you're looking at this here, that alpha must be equal to inverse, or a prime times inverse gamma, and that alpha prime is equal to alpha gamma, and alpha prime j is equal to sum over I alpha I gamma ij. So in other words, any transformation you make on the vector is instantly canceled out by within the operator. And so the alpha in this case seems to behave a lot like a vector. And so in other words, in order to get a, since we're starting out with a vector and we end up with a scalar, then if the x sub I is a column vector, then that implies that the phi, the alpha is actually a row vector. And that somehow those two vectors are combining together to give us a scalar. And that transforming one results in an inverse transform of the other. That makes sense? So this brings us to the idea of the scalar product. So the scalar product is where we might have A dot B, and that is also, by the way, the same thing as B dot A complex conjugate. And the scalar product commutes, where you might have the vector A dotted with lambda B plus mu C equal to lambda A dot B plus mu A dot C, or A dot A greater than or equal to 0. In other words, and so these are basically the products, or the properties of a scalar product, where you have that your scalar product does commute, so A dot B and B dot A are essentially the same. You do have this commutative property where if you sum together two vectors and you do a dot product, the same thing as just dotting each one. And that in the case of at least three-dimensional vectors, you're always going to get something greater than 0 when you dot it with itself. The only way that this is equal to 0 is A and B, or A is equal to 0 itself. Now we also have a property where A dot B is equal to 0 if A and B are orthogonal. We don't use the word perpendicular anymore. We're going to use the word orthogonal. And the reason why is because in physics, when you start expanding this beyond 3 dimensions, then the idea of perpendicular stops making any sense, what orthogonal does. And so what orthogonal means is basically this, that your dot product of those two vectors gives you 0. It also can mean, it's also not exactly the same as linearly independent, but it's kind of synonymous with that. And also you can calculate the length of a vector by just taking A dot B to the 1/2 power, and so we call that the magnitude of A, or the length of the vector A. And then also another thing is that for the most part, when you take two coordinate bases and you dot them together, they're going to be orthogonal. And that's called an orthogonal coordinate system where you see that. So in other words, X dot Y orthogonal, phi dot R or orthogonal, so on.
But is it dot by 0 or is it?
No, if they're different. Delta means that if they're different. So if they're the same, you get 1.
Gotcha.
If they're, and the thing is that what we're normally going to do is, by the way, this is not necessarily, I should use the word orthonormal here. And so what orthonormal means is it's orthogonal and it's normalized, so that you're essentially going to say all of your bases are going to be unit vectors. So they have a magnitude equal to 1. And then if you dot them with themselves, then you get a magnitude 1. If they are dotted with something completely different, then they're going to give you something different.
So that's the notation. All right. So the notation for the Crawford delta function makes sense now.
Yeah, yeah. Because the thing is, like, for the most part, I kind of use this general term where I did, use the general arrow, but this is why you're going to see them with the hats on them, because they're going to be unit vectors, for the most part. Okay. All right, I'm going to do some eigen. Let's see, 5:15. I think. Does everybody need a break right now, or do you want to pull through, do the eigenvalue stuff? How long? I'd say at least 15 to 20 minutes. You guys need a break? Okay. All right. We'll take a break, and when we get back, we'll do eigenvalue. All right, so the next thing I want to get into is eigenvalue problems. And so this is something, again, something you guys have probably seen before, and that is going to be, it's really useful to use, and I'm going to actually give an example from physics on how this could actually be used. But for the example I'm going to go into, I'm not going to go into extreme amount of detail on every little mathematical step. So the basic idea of an eigenvalue problem is that you have this thing called an operator, and it acts on a vector or an eigenvector, and the result is going to be some type of scalar value called an eigenvalue times that eigenvector. So these are the parts, operator, these two are the eigenvector, and this is the eigenvalue. And the neat thing about this is that for a particular operator acting on a particular eigenvector, you get particular eigenvalues. And this is actually, the reason why this is useful to us is because essentially this is how quantum mechanics works. Is that, at least in my understanding of quantum mechanics, what they've done is that in classical physics, you just simply observe stuff and that's what happens. And then they got it, formed them into differential equations, and these differential equations told you what's going on. With quantum mechanics, what they did was they just basically reduced everything down to an eigenvalue problem, where you want to know the position of a particle, it's an eigenvalue problem. You want to know its energy, it's an eigenvalue problem. And so they basically use this to solve pretty much everything in quantum. And so if you can solve these eigenvalue problems, it helps you out in quantum mechanics, and I'm going to give you a classical physics example as well. So we're also, by the way, we're going to have one of the weeks, about 2 weeks from now, we're going to have the entire lecture is going to be just over eigenvalue problems and how to solve these and approach these eigenvalue problems. And we're going to do them in a more general sense than just sticking to linear algebra. So the idea here is that if you're given a coordinate system, so let's suppose you take your eigenvalue problem and you reduce it down to summing over the matrix components with your eigenvector, and the result is going to be your eigenvalue times your eigenvector. Where here, I is equal to 1, 2, all the way up to n. And let me get rid of this. Sorry. So what happens is that you basically have your matrix times x, your eigenvalue is equal to, or eigenvector is equal to lambda times the eigenvector. And so you might have like some matrix A, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. And the way you can express this equation is you can write it as if you just have the matrix A minus the identity matrix times your lambda times x is equal to 0. Now, what happens is if A is given by this 3 by 3 matrix, then A minus I lambda is just going to be 1 minus lambda, 2, 3, 4, 5 minus lambda, 6, 7, 8, 9 minus lambda. And if you take that and you multiply it by x1, x2, x3 for the components of the column vector, result is 0. And so if the determinant of A minus I lambda is equal to 0, then that's going to satisfy this equation because the properties of the determinant are the same as the properties of the matrix. And so what you want to do is you want to calculate the determinant of this matrix. And so when you calculate the determinant equals 0, what will happen is you'll end up with 3 possible values of lambda which are going to satisfy this and give you, determinant equals 0. And so if it's an n by n matrix, there's going to be n roots, n different values of lambda that work. If there was a 4 by 4 matrix, you're going to have 4 eigenvalues. If it's a 2 by 2, you're only going to have 2 eigenvalues. So the number of eigenvalues you're going to get is going to depend on a number of terms. So then, once you find the eigenvalues, what you do is you plug each eigenvalue into the matrix here, and then solve this equation. And then, and by doing that, you're solving for x1, x2, and x3. And so as a net result, you're going to have, in that case, for a 3 by 3 matrix, you're going to have 3 eigenvalues. And then you're going to have, each eigenvalue is going to have its own set of eigenvectors. So, and that's going to, so you're going to have 3 different eigenvectors. Okay? Now here's where the magic comes in. The really cool thing about this, and the reason why this is actually useful, is because the eigenvectors, the 3 eigenvectors that you get out from this 3 by 3 matrix, are all going to be orthogonal to each other. And because they're orthogonal to each other, that means that they form a natural basis set. So they form a natural coordinate basis that you can use. And when you put the matrix in that coordinate basis using, so these become a basis for a coordinate system. When you use this basis and you transform your matrix that you got, the one that you use to calculate the eigenvectors, our eigenvalues and eigenvectors with, then what happens is you'll find that that matrix becomes diagonal, and these eigenvalues are going to be going right down the diagonal. So you end up with a diagonal matrix with all the properties of the original matrix. Just it's going to be in a different coordinate system. It's just going to have the eigenvectors as the basis. Can everybody picture that for a second? So in other words, let's see. I don't want to. What?
You have a coordinate system.
Yeah.
You can calculate the eigenvalues, and then you're just kind of like use that as your coordinate system.
Yeah, because another way of thinking about it is like in the general coordinate system. Like let's say you have this matrix A, okay, and you've got A11, A12, A13, etc. Okay? Now, after you calculate your eigenvalues, this matrix A, and this is like with, your basis is just going to be E1, E2, E3, etc., right? What's going to happen is after you calculate the eigenvalues, your new matrix is going to look like lambda 1, lambda 2, lambda 3, and the vectors are going to be like E1 prime, E2 prime, E3 prime. And just like before, all the bases are orthogonal to each other. It's just the bases are going to be the eigenvectors.
Would that make the values outside of the lambda diagonal symmetric?
0.
Oh, 0.
Even better. Yeah, so everything else here, zeros.
Yeah.
And so if these are all zeros, then if I want to calculate the inverse, it's just 1 over lambda. If I want to calculate the trace, I could do that. Just multiply, just add up the lambda values. If I want to calculate the determinant, I could just multiply the eigenvalues together. So the determinant of this is just going to be equal to lambda 1, lambda 2, lambda 3. And that's it. So this is the reason why we are going to use, this is why we use these things. Because if we can actually simplify the problem, then our life, becomes a lot easier. So let's see. And so what we can do then is and the way we could see that this works is that let's say we have a linear operator acting on some basis vector, and that gives you lambda 1 or lambda I times that basis vector. Then what happens is we're going to say that A prime ij is a component. So the ith component of the operator acting on the basis. So now what happens is we can say that, well, let's take A prime ij, and let's say that that is equal to taking E prime I times the operator times E prime j. And that works because we're basically just saying that if this is just the ith component of this guy, then we just multiply this component by the basis and we get, the full thing. So because of this eigenvalue relationship here, we could say that this is equal to E prime I, the eigenvalue E prime j, and then the eigenvalue is just a scalar, so this is just lambda j times the delta function. And so you can see here that the matrix is equivalent to just taking the delta function with the eigenvalues. So this is just a diagonal matrix. So A prime ij is a diagonal matrix of eigenvalues. So that's pretty cool, because that means that, you know, we just show that that works. And it just so happens that, you know, in this case, you could see that these are the eigenvectors that make all that possible. If we didn't use the eigenvectors, then it wouldn't work. All right. Let's see. And so because of that, they have the same trace, they have the same determinant. You know, like I said before up here, the trace is just summing down the diagonal. The determinant is just multiplying the diagonal components. All right, so let's do some physics for once, okay? So here's the problem. You're going to have 3 particles, and they're going to be organized like a triangle. This is going to be M1, this is going to be M2, and this is going to be M3. And each of these 3 particles is connected with a spring. And each one of these springs has a spring constant K. Okay? And so what we're going to do is we're going to create kind of this coordinate system where particle 1 can move in basically the x, y, and z directions. And I'm going to call this x1, y1, and then there's a z1 coming out towards us this way. Particle 2 is going to have, you know, same thing, y2, x2, and particle 3, you know, x3, y3. So this is a 3-dimensional system. And so the problem that we have is I want to know every single possible way that this thing can move. Okay? And this is where our linear algebra is going to come in handy, and our eigenvalue stuff. So if we've created a simple coordinate system where E1 is basically going to be mass 1 moving in the x direction. E2 is going to be mass 1 moving in the y direction. E3 is going to be mass 1 moving in the z direction. E4 is going to be mass 2 moving in the x direction. And I don't think I have to spell it out any further, right? So the idea then is that we've created this simple coordinate system. Now what we're going to do is we're going to, you know, we're doing physics, so we want to look at energy. And so we have that the kinetic energy is equal to 1/2 times the sum over I of mi x dot squared I. And that is equal to 1/2 times I dot transpose times the matrix x dot. So what this is basically saying this is kinetic energy. Kinetic energy is when you take a particle with a certain mass and it moves with the velocity squared and then throw a factor of 1/2 on it. And so mi in this case is the mass associated with whichever one of these positions. And x dot here is the time derivative. So x dot I is equal to the time derivative of xi with respect to time. And M is a diagonal matrix where that's going to come from Mij is equal to each one of these down the diagonal. So we're going to have like basically, you know, M1 is going to be, for the first three, and M2 is going to be the next three, and so on down the diagonal. And so if you do that, we've basically rewritten the kinetic energy as a matrix problem. Can everybody kind of agree with that?
You multiply the percentage scalar by its identity matrix and just treat it with matrices. It's not.
Pretty much, yeah. I mean, the whole idea here is this isn't like a unique way to do it. This is just basically saying that this is an accurate way of doing it, and it's a consistent way of doing it that we can, that works for us and works for whatever we're trying to do. So the kinetic energy is, this kind of falls back to the definition of kinetic energy is consistent. Now, also, we know that this is a vibrating system, so we can introduce small vibrations into the system. And I emphasize small. So the idea is that we also have not just kinetic energy, but we have potential energy. And the potential energy can be thought of as basically doing like a Taylor expansion about a certain point, because each one of these has got its rest position, and they're going to kind of vibrate about that position. So we have V naught plus the sum over I of partial V respect to xi evaluated at xi equals 0, xi, plus the sum over I and j of 1/2 partial second derivative with respect to v with derivative with respect to I and with respect to j. At xi equals 0, and just multiplied by xi, xj. And, and you could just keep going with higher and higher terms. So it's just a Taylor expansion. Now, here's the thing. We can set V naught equal to 0 because we only really care about differences in potential, and so we could say that at the origin there's no potential energy. We can also, we know that if you take the derivative with respect to potential, or derivative potential with respect to position, this is also equal to 0. This is also equal to 0. And the reason why this is equal to 0 is because the force is equal to 0. And we know that the force is related to the position derivative of potential, right? So this is because force equals 0 when this thing is at the origin. So now what we get is that the potential is basically equal to 1/2 times the sum over I and j of this second derivative term. And so I'm just going to write this as v I j xi xj. And that in turn could be written as 1/2 times the transpose of x, v times x, where vij is just the second derivative term. All right. And so you can see that this is a symmetric matrix too, right? So the next thing we want to do is, so now we have one matrix with the kinetic energy and another matrix with the potential energy. And by understanding kinetic and potential energy from classical mechanics, we could predict the motion of the particle. So what we can do then is we're going to change the coordinate system. Where in the new coordinate system, we're going to have a transformation matrix gamma, which is going to be like 1 over square root of M1, 1 over square root of M2, and it's going to be like 9 terms going all the way down the diagonal. And we're going to have our new coordinate system is basically going to be E prime is equal to 1 over square root of Mi Ei. So if we do that, then our kinetic energy, when we do our transformation, we have x dot transpose prime gamma times m gamma, this would be transpose of gamma, times x dot prime. And because of this term with the 1 over m's, they're going to cancel out the m matrix, and we're going to end up with just 1/2 x dot transpose prime x dot prime. And then for the potential, it's just going to take this matrix with the same thing. It's going to take our V matrix, and it's not going to eliminate it or anything, but what it's going to do is we're going to change it into another matrix, and we're going to call it A. All right. So A in this case is real and symmetric. And it's real and symmetric because V was real and symmetric. And real and symmetric means Hermitian. And remember, Hermitian means that we have real eigenvalues. And real eigenvalues are going to turn into real observables later on. So A, in this case, has got some real eigenvalues and real eigenvectors. And it's got n because it's an n by n matrix, and so in this case it's going to be 9 by 9 because that's the way our coordinate system works. So if you take A times UK, where UK are eigenvectors, it's going to give you lambda k UK, where these are the eigenvalues. And so what this means is that if we make a unitary transformation, so we're going to change E prime J, and we're going to change those into U of K. So we've made some kind of coordinate transformation. So we've gone from whatever the heck this basis is before to these eigenvalues. Then what's going to happen is that all of our xk's are going to also change into some new variable qk. And so now in this new coordinate system, t is just going to be equal to 1/2 q transpose q dot, sorry, times q dot here, which is essentially just equal to 1/2 times the sum over k of q dot k squared, and v is going to become 1/2 q times lambda q, where this is basically a diagonal matrix formed by the eigenvalues. So this is equal to 1/2 times the sum over k of lambda k qk squared. And so lambda, the capital lambda here, is the diagonal matrix formed by the eigenvalues. All right, so the eigenvalues are real and they're positive, since the potential is real and it's always positive as well. All right, so now this is where we bring in Lagrange's equations. Now, Lagrange's equations are basically, if you haven't had classical mechanics yet, it's the equations that you use in classical mechanics to get the motion from knowing the potential and kinetic energy. So, Lagrange's equations basically say that if you take the time derivative of the potential of the kinetic energy, or you take it with the derivative with respect to velocity, and you add to that the derivative of the potential with respect to position, the result is going to be 0.
You take the partial with respect to both T minus D's. Like the partial.
Oh, well, no, but the thing is that the potential doesn't depend on position, and the kinetic energy doesn't depend on velocity. So it doesn't. You don't really need to have all that in there. So this is kind of a simplified way of writing the Lagrangian. And so you remember that T is just 1/2 Q dot squared, right? And so when you take the time derivative of that, you end up with Q double dot. And then for V, that just basically reduces down to Q squared times the eigenvalues times 1/2. And so you take the derivative, you end up with just eigenvalue times Q equals 0. And then that's your answer. So this is basically the equation of motion for the particles. And so what happens is you get either the eigenvalue is greater than 0. If in that case, if it's greater than 0, you solve the differential equation. You get QK is equal to some value times the sine of omega kt plus lambda k, where omega k is equal to square root of lambda k. And what that means basically is that you have this harmonic motion where everything is oscillating. You know, and to get the particulars on that, we're going to take it a step further. And then the other possibility is that lambda k equals 0. And if lambda is equal to 0, then you basically have Q double dot equals 0, in which case QK is just linear. And so it's just going to be some constant times time plus some other constant. And so these omega k are called the normalized frequencies. So they're the normalized oscillatory frequencies that this thing naturally vibrates with in normal coordinates. And so you could call this a normal mode that they're vibrating in. And this is very similar to basically saying that, like, you have a crystal lattice and you hit it, and then there's a natural vibrating frequency that it has because of all the atomic bonds. For this lambda k equals 0, where you can see that QK just gets bigger and bigger, these are all rotations or translations of the system. So in other words, with time, the thing could be spinning, or it could just be moving, or the entire system just moves at once. And you'll notice that in order to find out what's really going on, we have to translate the system back. So we have x prime is equal to u prime q. X is equal to gamma x prime, which is equal to gamma u prime q, where u I k prime is equal to little u ik, which is equal to e prime I uk. And so then x sub I is equal to the sum over j and k of gamma ij u prime jk qk. And then this you can translate into the sum over k of 1 over square root of m I u I k prime qk, which is equal to the sum over k of u prime ik over square root of mi times ak sine of omega k t plus delta k. Now that is basically the sum over k of what I can just call uk or uik, where I've just kind of taken the u prime and I've divided out the mi term, and then I have the a k sine of omega k t plus our phase factor. And so you'll notice that what we do is we put all this in here, and then all of a sudden, by summing over all these different modes, we can get back to what is the position of each of the different particles at a time. Okay. So I know that this is a very hand-wavy way about going about it, and within classical mechanics, they can do this example in kind of a slightly different way. But the whole idea here was just to illustrate how you can use these eigenvalues and use the linear algebra in order to solve a real physical problem. And so you can actually, in like a numerical analysis, numerical methods, it's actually common that you can actually use linear algebra techniques to solve differential equations and things like that. Okay. Any questions? Like I said, I knew the eigenvalue stuff was going to get involved. That's why we have a separate week on that.
So essentially, you just use the Lagrange equation most of the time, use the weight.
Yep.
Most of the weight.
I just use Lagrange's equation, use that to define the actual motion. And then what comes out of this is that when you actually calculate this, you'll see how many are 0 and how many are greater than 1. But what happens in reality is that you've got 3 different ways that the system can rotate, because it has 3 different axes it can rotate about. And then it also has 3 different translational modes too, where you can just move the entire thing. And so that means that out of the 9 eigenvalues you can have, there's only 3 left for normal modes. And so you can kind of figure out how many normal modes you're going to have based on that and what they're going to be. Yeah. Yeah. And the thing about this is molecular vibration. This is only involving 3 particles. So you can imagine if you have like 1,000,000 particles. Then each particle adds essentially another 3 degrees of freedom into this system, which means that you're going to have like 3 million degrees of freedom. And then once you get rid of the 3 rotation modes and the 3 translational modes, now you've got 3 million minus 6 different oscillatory modes that this thing can experience. And what happens in like a crystal lattice structure is that you'll actually see that there'll be like a a dominant frequency where these things are vibrated with. So it'd be, all the lambdas end up coming out the same, and you end up getting one frequency here. So it's pretty cool because this actually tells you a lot about how materials work, or the mechanics of materials and things. Okay. Any other questions on this? Because the next topic we got is going to be a massive switching of gears. Okay. All right. So next up, I'm going to talk about non-Cartesian coordinate systems. So the idea here is that we're used to having everything in terms of x, y, z, and that's usually not how it actually works. One thing is we are going to be sticking to orthogonal coordinate systems, and an orthogonal coordinate system is one where each one of the different dimensions is going to be orthogonal to the other two. So we're still going to have, cross term x dot y is equal to 0, etc. And so the way that these systems work, and this is the way I always visualize it, is if you can imagine you have a cylinder here. And I take my cylinder and I add to that a Cartesian coordinate system. Okay? And I take my Cartesian coordinate and I just melt it over the cylinder. The result is going to be something that looks like this, where you can see that one dimension kind of curls around. And now, in this case, this is the z dimension. This is going to be the radial dimension, we're going to call rho. And this is the phi dimension, the angular dimension. And then you can do the same thing with the sphere. And the result is going to be you have two dimensions that kind of curve, and one that goes out like this. And so this is the radial dimension, this is theta, and this is phi. And so the idea is that, there's a relationship between all these guys. And you can see that in general, what they do is they use these things called generalized coordinates. Uh-oh. I left out a letter. R. And the generalized coordinates are typically like Q1, Q2, Q3. And what happens is you could say that x is equal to a function of Q1, Q2, and Q3. In other words, you're going to form the basis for the x coordinate off of the basis for these other coordinates. And the same thing for y and z. And so what happens is that you can kind of translate back and forth between x, y, and z in Q1, Q2, and Q3, where, in the cylindrical coordinates, the z is the same, but with spherical coordinates, they may be completely different. And so the idea is that you can associate a basis vector or unit vector with any of the generalized coordinates. So what you get is that you can have any vector which can be written in terms of v1 e hat 1 plus v2 e hat 2 plus v3 e hat 3. And you can differentiate by going dx is equal to partial x respect to Q1, or dQ1, plus partial x respect to q2 dq2 plus partial x respect to q3 dq3. And so you can see here that I can, if I want to know like how my coordinate x changes, I can do it with respect to these other coordinates. And I can do this because x is a function of q1, q2, and q3, right? So what I can do, what I use this for, is because I want to know the distance between 2 points in my system. And that's ds squared, and that's equal to dx squared plus dy squared plus dz squared. And in generalized coordinates, this is equal to g11 dq1 squared plus g12 dq1 dq2 plus g13 dq1 dq3, etc. And you can write that as just the sum over I and j of g I j dqi dqj. So in this case, gij is known as the metric, or a metric tensor. And so it is really the most important tensor that you need to know. And the reason why is because this metric allows us to specify exactly what coordinate system we're working with, because it explains essentially how our Cartesian coordinates relate to whatever the coordinate system we're dealing with is. And so gij is equal to partial x with respect to qi, partial x with respect to qj, plus partial y with respect to qi, partial y with respect to qj, plus partial z with respect to qi, partial z with respect to qj. And that is effectively partial xl respect to qi, partial xl respect to qj. What's the metric?
What is the metric?
Oh, all it is that relationship between the Cartesian coordinates and whatever your coordinate system is. So, and I'll talk a lot more about this, because we're not done talking about the metric. Yeah, I mean, next week you're going to be seeing the metric so much you'll be seeing it in your sleep. So the idea here is that if we're talking about an orthogonal coordinate system, then the metric is going to be such that gij is equal to 0 for I not equal to j. In other words, the metric, you can write it like a matrix, and this means that it's going to be a diagonal matrix. But the basic idea of the metric is that the metric is going to relate, it's going to define your coordinate system by relating your coordinate system to the Cartesian coordinate system, or vice versa. All right. So, you know, I think most of the time they actually have the metric defined the other way around, but the way that they did in Arfin and Weber, they define it this way, where it's the derivative of the Cartesian coordinates with respect to the generalized coordinates. But I think what everybody else does is they do it the other way, where it's actually the generalized with respect to Cartesian. But that's not important.
Yeah, I think that's when they use like delta R.
Mm-hmm.
They do this
associated right there in my practical. So we just know what we're talking about
Yeah,
there.
yeah. So the idea is that we have our basis where we have E hat I dot E hat J are different bases, and they're going to be delta function. And this is what you see in an orthogonal coordinate system. And so what we can do is, since this is an orthogonal coordinate system, we can replace the metric GII, because they're all I is always equal to J, with just the term HI squared, where each, and then you can just think about it in terms of H's. And so now ds squared is going to be equal to H1 dq1 squared plus H2 dq2 squared plus H3 dq3 squared, or sum over I of HI dqi squared. And so this also implies that ds can be written as the sum over I of HI dqi. And you know, some of your problems involve this whole H thing. So what happens is you can have a differential distance vector, dr, which is basically equal to the sum over I of HI dqi E hat I. And you can do a line vector where you have the integral of an arbitrary vector dot dr is equal to the sum over I of the integral of vi hi dqi. And so basically the whole idea here is that your H's are going to allow you, H's relate to the metric, and the H's are going to allow you to define a coordinate system.
What, is that where H is defined up there? Or is H?
H is defined right here.
Okay.
So H is, oops, let's see if I can, no, I can't undo that. Well, H is defined right there. Got a little sloppy. But we also have the area element, where the, if you want to integrate area, you could define that using H. It's basically just dsi dsj, which is equal to hi hj dqi dqj. And then you have your volume element, which is equal to ds1 ds2 ds3, and that's just h1 h2 h3 dq1 dq2 dq3. So you can use all that. And so the area elements are perpendicular to the surfaces. So in other words, if you have a surface like the surface of the screen, you would define the area element as a vector sticking out from the screen. And so what you get then is you can integrate a surface area by just simply integrating over whatever other vectors are there. Now, you can also use, you could do your vector algebra the same way you can do in all orthogonal coordinate systems. So, for example, A dot B is equal to just A1 B1 plus A2 B2 plus A3 B3. And A cross B is equal to, basically you just have this matrix and you just calculate the determinant of this matrix, and it's going to give you the cross product. And you could do other things with this too, like you can calculate gradients, where the gradient is, by definition, it's a vector quantity corresponding to how a scalar quantity changes with distance over direction. So the gradient, by definition, is something like E1, for the x direction of this, where this is a function of the generalized coordinates Q1, Q2, and Q3, and it would be given by essentially taking the derivative of psi with respect to S1, which is equal to 1 over H1 times partial psi with respect to Q1. And then you could do the same thing for the y and z directions as well. And then you could see that because we're already multiplying this by a basis vector, you can say that, well, the gradient of psi could be equal to taking E hat 1 over H1 partial psi respect to Q1 plus the same thing with the y and the z directions. So when you calculate your gradient, you're dividing by the h term. That's why it is that in Cartesian coordinates, when you're calculating your gradients, it's just taking a straight derivative with respect to x, y, or z, right? But in spherical coordinates, when you take your derivative with respect to theta, you've got this 1 over r term. With the phi, there's the r sine theta term, and that's coming from the h's. And you can also do the same thing with divergences, too. Because the divergence is basically, it's a vector quantity that changes with direction. And so to calculate your divergence, you actually are going to have, it's essentially the limit as delta tau goes to 0 for the integral of v dot d tau divided by the integral d tau. And so, this would be d sigma here. And so what happens is they use Gauss's theorem, which takes the integral of the divergence of a vector integrated over volume is equivalent to the integral of the vector integrated over a closed surface. And so when you calculate the integral of v dot d sigma, what happens is you're going to get something like the integral of, the derivative respect to Q1 of V1 H2 H3 plus the derivative respect to Q2 of V2 H1 H3 plus same thing Q3 V3 H2 H1. And that is going to be integrated with dQ1, dQ2, dQ3. But this bottom integral, with just respect to volume, is just going to be equal to the integral of H1, H2, H3 of dQ1, dQ2, VQ3. And so the net result is going to be that your divergence of a vector is going to be like 1 over h1, h2, h3 times these partial derivatives with respect to q1, well, v1, h2, h3, etc. And then when you take a Laplacian, that's just basically going to be something similar to that, because it's just basically a divergence of a gradient, and so you end up with partial respect to q1 of h2 h3 over h1 of this derivative of psi. And so the neat thing about this is that it basically, and I could keep going on, but they do the same thing with the curl, and they do the same thing with other functions. So you end up essentially every single one of those formulas that you see in the inside cover of like an electrodynamics book, where it has the derivative of or it has like a divergence of a vector in spherical coordinates or something like that, you can derive from here by just knowing what the h's are. Oh, one more, the curl is like 1 over h1, h2, h3 of this matrix thing. And I'm not, just in the interest of time, I'm obviously not going to go through every single derivation here. But when you have time, what I recommend everybody do is actually read through the relevant sections in Arfken and Weber, because they do the best job of actually understanding where this comes from and how you would actually derive this stuff. Okay, B1, B2, B3. All right, so you'll notice that if you use a Cartesian coordinate grid, these basically come out exactly like you would expect for, because H1, for Cartesian, H1 equals H2 equals H3. So this is kind of boring. They're all equal to 1. And so the net result is that the divergence is just straight derivatives, the gradient is just straight derivatives, etc. But the neat thing is when you get to something like, I'm just going to do cylindrical coordinates. In cylindrical coordinates, H1 and H3 are both equal to 1. But H2 is equal to rho. And so because of that, when you calculate your gradient, it's going to be like rho hat partial psi respect to rho plus phi hat 1 over rho partial psi respect to phi plus z hat partial psi respect to z. And when you calculate your divergence, it's going to be 1 over rho partial respect to rho of rho v rho plus 1 over rho partial v phi respect to phi plus partial vz respect to z. And so you can see here where the rows just kind of popped in, and they only showed up because of the H values. And then you could do the same thing with the Laplacian, where it's equal to 1 over rho, partial respect to rho, of rho partial psi respect to rho, plus 1 over rho squared partial psi, second derivative of psi respect to phi, plus second derivative of psi respect to z. So you can see here, just putting in the H values changes everything, and that's just basically just saying we just put in a different coordinate system. Now I'm not going to do the spherical coordinates, but pretty much the same thing happens there. So anyway, what I would like everybody to do, on Thursday at recitation, we're going to have time to ask specific questions over any of the stuff you guys have or any of the homework. But in the meantime, if you would like, what I suggest that everybody does is that you read through the chapters in Arfin and Weber, and I think it used to be like at the beginning of the book, but I think it's chapter 3 or something like that, if I'm not mistaken. Yeah, it's chapter 2 and 3, and there's a little bit in chapter 1.7 in Arfin and Weber, and you should look at that because in the next lecture next week we're going to get into tensors, and this is a very good lead-in to understanding the tensors. So we're going to be talking a lot more about the metric, and we're going to be talking a lot more about different coordinate systems and changing coordinate systems and things like that. All right, any questions? This is a lot of stuff for one day. All right, if nothing, I guess I'll see you guys next week. I'll see you guys on Thursday.